All right, homework number 14. This is our homework assignment that goes with the integral test. So it says confirm that the integral test can be applied to the series and then use the integral test to determine the convergence or divergence of the series. So remember, the integral test does not find the sum of the series, just the fact that it converges or diverges. I left the conditions up here for integral test. So confirm that it can be applied. You define f of x as the same function as the series, just to replace n with x. And I'm just in my head verifying that on this interval 1 to infinity, f of x is positive. So e to the x is positive, so this will be positive. Continuous, e to the x is never 0, so there will not be issues there. And decreasing, meaning the terms are approaching 0. So all of that is true. So that means that we can set up an integral from 1 to infinity, but let's make this b, and we'll make it the limit as b approaches infinity. So I always treat these like free response questions, because if you do the shortcuts like you would for multiple choice, you will probably forget the correct way to do it for a free response. So anyway, limit as b approaches infinity of the integral from 1 to b of e to the negative x dx. And I need to use u sub here. So u is equal to negative x. Du dx is equal to negative 1. So negative du is equal to dx. So we're swapping out a dx for a negative du. So this is going to be the limit as b approaches infinity of negative integral 1 to b of e to the u du. All right, and then we will integrate. So negative, the integral of e to the u is e to the u is negative x, so it's going to be e to the negative x, or I'm going to make that 1 over e to the x. When you're evaluating by plugging in infinities or zeros, it's a good idea, really any number, I guess, it's a good idea to rewrite your negative exponents as positive exponents in a denominator so you get the correct values when you take the limit. And remember, we're supposed to show the fundamental theorem, which is plugging the numbers in before you evaluate the limit. So this would be 1 over e to the b minus 1 over e to the first. Now I can take the limit. 1 over infinity is 0 minus 1 over e. And this negative gets distributed through, or maybe you had it in your antiderivative already. So this would be 1 over e. So remember, this is what the integral converges to. This just tells me that the series from 1 to infinity of e to the negative n converges. So converges by integral test does not converge to 1 over e. All right. Okay, so let's look at the next one. So again, the conditions for the integral test are met. F of x is equal to x. I just made it over e to the x over 2 instead of the negative exponent. Both of those terms would be positive if you're plugging in 1 and beyond, continuous and decreasing. So I will go on with my integral. Again, it's going to be the integral from 1 to infinity. So I'm going to make b approach infinity. And I'm going to make this x times e to the x over 2. Negative x over 2. Now, for this one, u sub does not work because u would be negative x over 2. So du would be negative 1/2, which is not going to cancel this x out. So this is integration by parts. We have an algebraic and an exponential. And it will be integration by parts if, notice how the exponent is the same degree as the expression out here. So that's why u sub is not going to work. If this were negative x squared over 2, then u sub would be the option. All right, so I'm going to do the tabular method for integration by parts. So I need to let, based on Liate, the algebraic piece should be the u, and that means the e to the negative x over 2 dx, that will be dv. Remember, you're integrating this side and you're taking derivatives of the left side. So take derivatives of x until you get 0. When you integrate e to the negative x over 2, you're going to get e to the negative x over 2. And then u sub, du would have been negative 1/2 dx. So there's going to be a negative 2 that gets multiplied out to satisfy that. So just like back here, when du dx was negative 1, there was a negative sign out here because I had negative dx. If this was negative 1/2, I'd have a negative 2 out in front. So same idea. If you need to do the full out, u sub off to the side, then definitely do that. But otherwise, if you can do this in your head, there it is. I need to do that one more time. So the same thing is going to happen. I'm going to multiply by negative 2 again and get 4 e to the negative x over 2. Put in your plus, minus, plus. Connect your diagonals. The swoop at the bottom represents the integral of 0 times 4 e to the negative x over 2. So there won't be any integral left over from this. We still have a limit as b approaches infinity, and this is going to get evaluated. So I'm putting all this in braces. So x times negative 2, so I'm going to make that negative 2x e to the negative x over 2. And then minus 1/4 e to the negative x over 2, evaluated from 1 to b. I'm going to rewrite my negative exponents as I plug in the values here. So this is negative 2x on top, and then it would be e to the b over 2 minus 1 over 4 e to the b over 2. So that's the first term you get when you plug in b. And then minus, plug in 1, so negative 2 over e to the 1/2, and because I sent this down already, and then minus 1/4 e to the 1/2. Don't work too hard on the math. Remember, you're just trying to say, does this come out to a number or does this come out to infinity? So this one is, we wouldn't have to show L'Hopital's method in here. I've checked on that before. Technically, it's infinity over infinity, but exponential function races are going to win out over linear. So we have 0, minus 0, the first term, and then minus, these are just numbers, right? Actually, I'm just going to distribute the positive through. So I guess I don't have to, but plus 2 over e to the 1/2 plus 1 over 4 e to the 1/2. So I can do the math and combine this if I want, but the idea is that the integral converges. So I know that, well, let's see. Let me make this note. Well, no, never mind. This is fine. So the integral converges. So I'm going to conclude that the original series converges as well by integral test. All right, so let's take a look at number 8. This one has some terms that we need to come up with a formula for. All right, sorry about that. This one has some terms that we need to come up with a video for. So start by listing out what the terms are. So n equals 1, 2, 3, 4, 5. I could have started at 0, 1, 2, 3. It doesn't matter. You just need to come up with a series that works. So what is the pattern here? It looks like if I double the n and then add 1, I should get those numbers in the denominator, right? 2 times 1 plus 1, 2 times 2 plus 1, 2 times 3 plus 1, 2 times 4 plus 1, 2 times 5 plus 1. So this is 1 over 2 times n plus 1. All right, and again, this is not geometric. It's not, I can't split it into the difference of two fractions to make it be telescoping. So we need to use integral test where f of x is equal to 1 over 2x plus 1. All right, so for x values greater than or equal to 1, this expression is positive, continuous, and decreasing. So I'm going to set up the limit as b approaches infinity of the integral from 1 to b of 1 over 2x plus 1 dx. So this needs a little bit of u sub. U is 2x plus 1. Du dx is equal to 2. Du divided by 2 is equal to dx. You can cross that out here if that makes it easier. This is u. So we're going to get the limit as b approaches infinity of 1/2, that's because of this 2 here, times the integral from 1 to b of just 1 over u du. And then that is the limit as b approaches infinity of 1/2. The antiderivative here is the natural log of the absolute value of u, which was 2x plus 1. Do fundamental theorem of calculus, which says we're allowed to evaluate by plugging in ln of 2b plus 1 minus ln of 2 plus 1, 3. And now we can take the limit. So the limit, as I plug in infinity, I get natural log of infinity. So this is infinity. 1/2 times infinity minus ln 3 is still infinity. So because the integral diverges, it means that our series 1 over 2n plus 1 diverges as well. So it diverges by the integral test. Okay, for number 9, same thing, we need to come up with what the series is. Now, don't make it too hard on yourself. You can start n wherever you want. And usually I start at 1, but this one it makes sense to say n is 2, and then 3, and then 4. So you can say we're going from n equals 2 to infinity. The integral test, it does not matter what this bottom constant is. You're still going to be able to integrate. So this just looks like it's ln of n over n. So for f of x equaling ln of x over x, if we plug in x values greater than or equal to 2, we get positive values. They're continuous and decreasing, approaching 0. So we can go ahead and do the integral test here as well. So the limit as b approaches infinity of the integral from 2 to b of ln x over x dx. We've seen this before. This might have even been in our notes. We know that, do u sub over here. U would be ln x. Du dx would be 1 over x. So either you can recognize that you have du, or you can solve this. So get dx by itself and replace dx with x du. So those cancel. This is u. So now it's the limit as b approaches infinity of the integral from 2 to b of just u du. So the antiderivative will be u squared over 2, but let's replace u. So ln x squared over 2, evaluated from 2 to b. And we're going to run into the same situation we had before. I want to show all my formal steps here. So fundamental theorem of calculus is ln b squared over 2 minus ln 2 squared over 2. And then evaluating the limit, this is infinity squared over 2. So infinity minus a constant is infinity. So this series from 2 to infinity of ln n over n diverges by integral test. All right, for number 17, this is unusual. We don't usually see inverse trig in our integrals, but arctan, remember arctan, as you approach infinity, that graph is just going toward pi over 2, whereas x squared plus 1 will keep growing. So these terms are decreasing. They are continuous, and they are positive. All right, so we want the limit as b approaches infinity of the integral from 1 to b of arc tan x over x squared plus 1. Now, we're used to seeing 1 over x squared plus 1 and saying the answer is arctan, but that's because 1 over x squared plus 1 is the derivative of arctangent. So this is a u sub. Like I said, we don't see this too often, or we haven't seen this too often. We need to let u equal arctangent of x. And du dx is equal to, it's technically u prime over 1 squared plus u squared, but u prime would be 1 over 1 plus x squared. All right, so we're used to seeing this in the integral. This makes sense, right? We're used to seeing the integral of this, and our answer is arctan. That's because if you take the derivative of arctan, you get this. Okay, so that is going to cancel nicely because you would multiply x squared plus 1 times du. So if that's what dx is equal to, the x squared plus 1s are going to cancel out. So we are back to having the limit as b approaches infinity of the integral from 1 to b of just u du. Right? So this is going to become the limit as b approaches infinity of u squared over 2, but that's arctan x squared over 2 from 1 to b. And we can do our fundamental theorem, which just allows us to evaluate this. So this is going to be arc tan b squared over 2 minus arc tan 1 squared over 2. And now I can evaluate the limit. So the arctangent of infinity is pi over 2. But remember, you're putting that into a squared piece, then dividing by 2. And the arctangent of 1 is pi over 4, again, squared over 2. So this is going to be pi over 4 divided by 2. Pi squared over 4. I bet I didn't do that in my key. Pi squared over 4 over 2 is pi squared over 8. This is going to be pi squared over 16 over 2. So minus pi squared over 32. That means that because the integral converged to this value, the series also converges to this value. So converges by integral test. Let's see. Did I square those pi's? I bet I did not. I'm going to have to fix my key to post. Oh, I did. Look at me. Okay, never mind. I did it. All right, number 20. Oh, okay. So I stopped erasing my work here because these just need explanations. So for 20, the directions say, no, never mind. We're in the same set of directions. This is the only one so far where the integral test doesn't apply. And that's because actually it fails the nth term test. So the terms are positive and they are continuous, but this is not decreasing to 0. The limit as n approaches infinity is equal to 1. So even though those terms are decreasing toward 1, they're not decreasing to 0. And that's the first requirement before you do any other test. So really this series diverges by nth term test because the integral test doesn't apply. All right, number 27, explain why the integral test doesn't apply to this series. Now this is an alternating series, remember, where the terms are going to go like this. So even though they might be approaching 0, which they are alternating. So this function would not be strictly decreasing, even though the terms are approaching 0. So that's why that doesn't apply. And then for 31, use the integral test to determine the convergence or divergence of the P series. So the next set of notes, we're going to talk about a shortcut for P series here. But we did talk about P integrals back in chapter 8. So here's the idea. F of x is 1 over x cubed, which is positive, decreasing, and continuous for values greater than or equal to 1. We know that the integral from 1 to infinity of 1 over x cubed is convergent. It's a convergent P integral. And if I remember correctly, the sum is like, if this is 1, the sum is like 1 over P minus 1, right? This should add up to 1/2. And so by the integral test, if this P series converges, if this P integral converges, then we can call this a P series, and it converges by the integral test as well. So we're going to look at that rule. It's a very quick test. We'll look at that rule in the next set of notes. All right, that finishes up this homework assignment. Please come into office hours if you want more practice with any of this or if you have any questions.